Two-tailed hypothesis tests a non-symmetric example. In this example, it is thought that the proportion of cats with a particular gene is 20%. A scientist believes that this value has changed. A random sample of 20 cats is tested for the gene. It is discovered that 12 cats have the gene. We're going to run a two-tailed hypothesis test at the 10% significance level to test if there is evidence of a change in the proportion of cats with the disease. This information here will give us our H0. This information will help give us our alternative hypothesis H1. This will give us our information N for our distribution. And here we have our test statistic. Here we set up the distribution. We define our discrete random variable. X is the number of cats with the gene. And we identify our hypotheses H0 and H1. We make sure that we define P, and we include the word population in our definition. We then set up the distribution symbolically. X has a binomial distribution where n equals 20 and the probability equals 0.2. We're going to solve this problem using two methods. Method 1, using p-values. We calculate the expected value, i.e. the number of cats we expect to have the gene, and this is the average or the mean number of cats with the gene. The expected value is equal to NP, which works out to be 4. We then compare the observed value, i.e. the test statistic, the number of cats who actually have the gene, with the expected value, which of course is 4. As 12 is greater than 4, this result, this test statistic, is in the upper tail, so we only actually need to focus on the upper tail. We calculate the p-value and we compare this to half of the original significance level because this is a two-tailed test. The p-value is equal to the probability that x is greater than or equal to 12, which works out to be definitely less than 5%. Use your graphical calculator to work out this value. This means that the result is significant at the 10% level. There is sufficient evidence to reject H0, and there is sufficient evidence to suggest that there has been a change in the proportion of cats with the gene. Make sure that you compare your p-value with half of the significance level, as is the two-tailed test. And in your conclusion, make sure you refer to the word change. Even though the result is significant and we're only working in the upper tail, we do not say that there is evidence of an increase. We are not testing for an increase. Our alternative hypothesis H1 was testing for a change. Method 2 uses critical regions. As the observed value 12 is greater than the expected value 4, we are working in the upper tail, so we only need to find the values in the upper critical region. However, just to practice, we will also find the lower critical region as well. The upper critical region. We need to find critical values C such that the probability of being greater than or equal to these values is smaller than 5%. Which is half of the significance level, because remember, this is a two-tailed test. Using a graphical calculator, we then find the value. If we work out the probability that x is greater than or equal to 8, we find that this is 3.2%, which is less than 5%, which means that 8 and all values above 8 are critical. We then need to check if 7 is in this critical region. So if we work out the probability that x is greater than or equal to 7, this works out to be 8.7%, which is bigger than 5%. So 7 and all values below 7 are not critical. So our upper critical region consists of the values 8 all the way up to 20. We do not actually need the lower critical region, but we're going to find it anyway. For the lower critical region, we need to find critical values C such that the probability of X being less than or equal to C is lower than 5%, again, half of the significance level. We can test various values, and what you will find is that the probability that X is less than or equal to 1 is 6.9%, so 1 is not in the critical region. This then leaves 0. There are no values lower than 0, so we wouldn't write the probability that X is less than or equal to 0. We just write the probability that X equals 0, which is 1.2%, which is less than 5%, which means 0 is in the critical region. So our lower critical region simply consists of the value 0. Our conclusion to the test using method 2. As the test statistic, the observed number of cats with the gene is 12, we note that this is in the critical region. Remember, we only need to worry about the upper critical region in this example. This means that the result is significant at the 10% level. There is sufficient evidence to reject H0. There is sufficient evidence to suggest that there has been a change in the proportion of cats with the gene. It is the same outcome that we achieved using method 1 and the p-values. Some further key points on this example. Notice that the two critical regions are of different sizes, i.e. they do not contain the same number of values. This is because this test was not symmetrical, because in the original distribution, X, which was a binomial distribution which had an n value of 20 and a probability of 0.2, the probability value is not 0.5, it was 0.2. The true value of the significance level for this test is not 10%, even though this is the value we were aiming for in this question. If you look at the lower critical region, the probability of X being equal to 0 was 1.2%. We were trying to find the values which would take us to an overall probability, a cumulative probability, that was as close as possible to 5% without exceeding it. For a discrete distribution, we will never get exactly 5%. The closest we could get was the probability of X being equal to 0, which was 1.2%. The same with the upper critical region. We were trying to find critical values C such that the probability of X being greater than or equal to C was as close as possible to 5% without exceeding 5%. The closest we could get was the probability that X is greater than or equal to 8, which is 3.2%. If we went down to 7, as you saw from the previous slide, we go above 5%. So our true significance level is 1.2% plus 3.2%, so 4.4% overall. This is illustrated on the next slide. This is a graph of the probability distribution for X, a binomial distribution, with n equal to 20 and p equal to 0.2. As you can see, it's a skewed distribution. There's a horizontal line drawn for p equals 5% or 0.05, and you can see that because x equals 1 has a probability that exceeds 5%, we only have 0 in the lower tail. Again, in the upper tail, we have the values 8 all the way up to 20. And you can see we can never quite get to 5% in either tail, and the closest we could get overall was the 4.4% described on the previous slide.